All right, guys, give me a minute to get set up here. I'm trying to make sure I get everything lined up. Okay. Well, welcome back, guys. You can hear me? All right, so I sent you all a email to sort of summarize some of the things that came up after our last meeting. And since then, do you have any comments or questions on what was in that? Anything I need to clarify? Oh, somebody says you can't see me. Is my video off? You guys see me or no?
Yeah, no, I can be you.
You can't see me?
No, I can see you.
Okay. Okay, cool. All right, good. So listen, one little change that I didn't anticipate was that it was either the Met Department or the university-wide IT, they set up this waiting room thing. I think that this is another one of their attempts to prevent Zoom bombing. I think I've now got it turned off, but that will probably happen every time now, is that you guys will have to wait until I actually disable it, which I can't do until the meeting starts. So I apologize for that, but I think that's the way that's going to have to go. One little sidebar I wanted to share with you guys. Let me share a screen with you. There. You guys see a picture of a lamp? That's not actually a lamp. That's, well, it was a lamp, and that's my webcam attached to the front of it. And the reason that I show this to you is I wanted you to see the number of things that can be varied in the way I've set this thing up. This is a swing arm lamp, and so it can pivot around an axis over here. And then there's an axis in here that can be rotated around this. You can rotate around a second one here, another one over here. There's a rotating point here and here and here. So I think I counted a total of 7 axes of rotation. And if, for example, I pivot this thing, if I lower the arm right here, then the part that connects this to the base would stay immobile, but everything from here further out would shift. And in particular, it would move the head of my camera, so that thing would move up and down. So let me switch back to there, the normal. So if I swing that arm up and down, of course, as you can see, it's moving my camera go up and down. So why do I care about this? Well, let me switch back to the document camera. Okay, so the point that I wanted to make with this is, first of all, happy April Fool's Day. By changing all of these different angles that were in the swing arm, you could, in order to tell somebody exactly how you had it arranged, you would have to measure each one of these angles of rotation around the different axes by giving somebody a number that represents how much you've rotated it from some initial resting position. So you have, I think I counted a total of 7 different angles that can be varied, which is to say, you can describe the position of this swing arm lamp by specifying 7 variables. So each position of the thing is now an element of 7-dimensional space. After you swing all of those different angles to whatever number you are told, in other words, if I told you the angles that you would have to set the thing to, then this little camera here at the head would be in a certain spot in space, and it would be staring off in a certain direction. So there would be several things that I could measure about that, I could go to a spot that's right inside the lens and measure the position of this point, which would be an element of three-dimensional space. It would be an element of R3. But furthermore, there's something else that I could measure, which is relative to that point. Imagine drawing a sphere around that point. Then the direction of the vector that comes straight out of the lens, in other words, the single point that you're focused on, that could be thought of as a point on the sphere. Tell me the latitude and the longitude of the point where this vector or this ray pierces such a sphere. So you get this latitude and longitude, which would then be an element of R2. And then there's one more thing that is being fiddled with as the swing arm moves around, which is I can rotate the camera around this without changing the position of the center of mass of the camera, and without changing the point that I've got it focused on. I can kind of rotate things like this through one more angle. So that would be this angle of rotation that you would see on the screen. It's telling you how much I have to twist things to get everything lined up the way I want it. That amount of rotation, that's an element of the real number line. It's an element of R1. The point of all of this is that my maneuvering the lamp itself changes what you guys are going to see, because it's the mechanics of the arm are determining a function that goes from seven-dimensional space, and it creates for you an element of six-dimensional space. The seven things that go in are the seven angles that I use to measure the positioning of my lamp, and the six things that come out are the three coordinates for your position, two coordinates for the point of focus on this sphere, and the last number is the amount of rotation around that point. So we refer to this six-dimensional space here as, what do they call it? It's the state space for the camera. It kind of tells you where the camera is and how it's pointed. And it's a familiar thing to people who do kinematics. If you guys have ever taken one of those virtual reality rides where you sit inside a little booth and they give you images of a roller coaster in front of you, and then they move the thing so that it feels like you're on a roller coaster, they're doing the same thing. They have to first move your body in space. Your center of mass is moved forward or back, left and right, up or down. So that's three things that are manipulated. But then even relative to where your center of mass is, there's a total of three different kinds of orientation. Two more things that would say, okay, without moving your center of mass, what should we be having you look at? And then finally, when you're in the same position and looking at one thing, you can still be rotated around in space like the astronauts in space. They do a full 360 without taking their eyes off you. They rotate themselves around. So this six-dimensional, the fact that this is a six-dimensional space is really, it's a constant thing in a lot of kinematic calculations. I needed to make sure that I bought a lamp that had at least 7 angles of variation to make sure that I could get, or sorry, at least 6 angles that I could vary to make sure that I had a reasonable chance of getting every possible orientation of my camera in space, so that I could, you know, keep wiggling things all around, closer and further, left and right, twisting this way and this way, that way. So to get every possible orientation to make my document camera work and be able to be turned back into an ordinary camera focused on me, I had to make sure that this number was at least equal to 6. If I'd have had something that had a smaller number of variables, then a function like this would be giving me a parameterization within the six-dimensional orientation space, but I would only be getting a surface's worth of possible orientations to the camera. When you have a function from R1 into R6, you're parameterizing a curve within that six-dimensional space. If you have 2 degrees of freedom, you'll parameterize a surface. 3 degrees of freedom parameterizes a 3-dimensional subset of the 6-dimensional space. That's not everything yet. You're still pretty limited. But once you have at least 6 things that you could vary independently, engineers call that 6 degrees of freedom. Mathematically, we're just saying that you have at least a 6-dimensional range of options, and that's what you would need if you wanted to cover 6-dimensional space. So that's not really a part of the course, but I just thought you guys would be entertained by taking my perspective and seeing not a swing arm lamp, but rather something that gets me to a lot of points in the 7-dimensional space. All right, so that was just me entertaining myself. Let's get back to the course. So a couple of things you need to know. You had a homework that was due last night, and then I changed the due date so that it is tonight. We spent some time on our last meeting going over one of the homework problems in that. Did anybody have any other questions relating to the homework that's due tonight? This will be your last chance to get something clarified. Okay, good, because I don't see any hands going up. Oh, by the way, if you do want to raise your hand, remember you have to use the little raise hand icon, because actually raising your hand wouldn't help unless I just happen to be looking at you at that moment. The next thing is the next homework. I put up a bunch of problems that's due a week from tonight. Let me encourage you to get started with some of the questions that are in there, but I got to warn you, people have already been pointing out that I'm having some trouble meshing the old syllabus and the new timetable and the set of problems that I've picked out. So I think some of the questions on that new homework set we're not going to get to them in time by next Monday or Wednesday. So try the ones that you think you can do and ask me about them at the meetings or in office hours. I will, occasionally I'll just tell you, you have to wait on that because you've asked a good question, but we don't have the tools to answer it yet, okay? And then when it gets to next Monday or Wednesday, I'm either gonna have to, remove some of the questions from this homework or else delay the due date on the homework to, I don't know, Friday or Monday or something. Okay, so don't freak out if it looks like some of the questions are too hard. But we do have to talk about Fubini's theorem. That's where we left off last time. So let me tell you about Fubini's theorem. First of all, guess what? It's a theorem. And that means that it has certain conditions. Every theorem has hypotheses. This theorem is only true under certain conditions. For us, those conditions are automatically going to be met. So I'm not going to ask you guys to worry about that kind of thing. But the conditions of Fubini's theorem would show up if you had some functions that were not continuous, for example. But in a nutshell, if the conditions of the theorem were met, some additional hypotheses. But if you start off with a function that's defined on the plane or a portion of the plane, and it's a real valued function, it just gives you a single number out. So that's the kind of function that's involved. This is going to be about integration, so you know that in addition to having a function, you have to be given a subset S of the domain of the function. And in particular, I'm going to call the subset not S, but R, because I want this to be a rectangle that's lined up with the axes of two-dimensional space. When you have a rectangle that's lined up with the axes if it's lined up with the axes, you can write it in the following way. So what you see me using here is the notation for intervals twice with a little multiplication sign between them. What this refers to is the rectangle of all the points in the xy plane whose x-coordinate comes from this first interval and the y coordinates come from the second interval. So here on the x-axis, let me draw the interval that goes from A to B. And then on the y-axis, I'll draw the interval that goes from C to D. And I want you to find all the points whose x-coordinates are in here and their y-coordinates are in there, and that would be this rectangle. And it's automatically lined up with the coordinate axes. So if you've been given a function defined at least on this much of the plane, if it's defined over the set R, and somebody asks you to take that function and integrate it over that rectangle, then the first thing you should recognize is you have to remember what it is that they're asking you to compute. So that's what we discussed last time, exactly what this represents. And I really want you guys to remember how to think of this. So it's not part of Fubini's theorem, but just exactly what the notation means is it's supposed to be a kind of a limit of a sum of products. It's a product of, you take a size of a piece of, well, in this case, it'll be a piece of the set R, multiplied by the value of the function f somewhere inside that piece. So remember, the process that we went through last time was we talked about taking the set R, splitting it up into a bunch of little pieces, and then within each one of those pieces, you choose a representative point where you evaluate the function, multiply the value of the function times the size of the piece that you just computed a product. You do that one piece at a time and you add them all up. And you've just computed what's called a Riemann sum. And you take the limit of such calculations where these sizes go down to 0. So the areas will go down to 0 in the individual pieces. Actually, you need to make the diameter of the piece go down to 0, but don't worry about that. That's the kind of integral that you're computing. If you do that in this setting, when you break a rectangle up into a bunch of little pieces, the way to measure the size of the rectangle would be the area of the rectangle. So the notation we will use is to put dA. You're multiplying a value of the function f times an infinitesimal amount of area. Okay, and that's what this set of symbols is supposed to represent. Now, Fubini's theorem tells you, here's how you can compute it. You can compute it as an iterated integral, where you integrate as y goes from c to d. And then you're going to integrate some function of y. Ooh, I'm going to have to draw it kind of small in here. And you'll integrate with respect to y. And the function of y that you're going to integrate is, well, you take this function f, which is a function of two variables, integrate that just with respect to x, but it'll be a definite integral as x goes from a to b. That's those two numbers. And when you integrate this function of x between those two values of x, you will get a number. It will be something that has no x's in it anymore. For those of you who remember computing integrals from Calc 1, and I hope that's everybody, you know that in practice, the way you do that is you anti-differentiate with respect to x, and then you plug in this value of x and that value of x, and you subtract, and there's no x's left. But all the way through those calculations, there will be y's floating around. Anything that's not an x is treated as a constant. So you will see y's in there, but you just leave them as if they were a pi or a 4 or any other constant. So in the process of computing this integral, you'll have y's floating around, and this will then be a function of y. And that is the function of y that you integrate with respect to y between those two values of y. And so at the end of the day, what you will get will be a number. So this is the content of Fubini's theorem in here. Fubini realized that you could compute one of these area integrals as an iteration of two one-dimensional integrals. So let's do an example of that to make sure we're all on the same page. So suppose that I ask you to take, let's have one of our saddle surfaces. That would be a function of two variables, and I might ask you to integrate this over a rectangle. Let's suppose that I ask you to take x's that go between 0 and 2, and y's that go between 3 and 6. So so I'll put the little dA at the end to remind you that we're going to use area as our measurement of what size means. So before you do anything else in this integral, please take a moment to just visualize what it is that you're computing. What the heck is the integral is supposed to give you. If you draw the graph of this, and by the way, I sent you guys a little link of a URL you can go to get some pictures. I'll invite you to play with this, but this would be, the graph of this would be one of those saddle surfaces. This function is positive everywhere in the first quadrant, but it's, and the third quadrant as well, but it's negative on the second and fourth quadrants to make that little saddle. You've seen me stand in front of you. I won't do the pantomime in front of this little camera, but this function rises to be positive everywhere in the first quadrant, and then it gives me places for my legs in the second and fourth quadrant. So roughly speaking, the graph would look something like this. The first quadrant is nearest you. The function is equal to 0 if you're on either axis, but then it rises in higher and higher as you move into the first quadrant, and also it's high in the third quadrant, but it's dipping down in the second and fourth quadrants. Now, that's the graph of this function, and I'm asking you to look at the points where the x-coordinates go between 0 and 2, and the y-coordinates go between 3 and 6. So that would be a rectangle over here somewhere. And this integral asks you to compute the volume of the region that lies under the saddle surface and over this rectangle. And I'm sorry if my picture doesn't make it clear, but this function is positive everywhere in this region. So it literally is going to be a region that's under that surface. You're under a saddle surface, but lying over this rectangle. The reason that I'm making you do the geometry first is I would like you guys to get in the habit of estimating your answers before you start. That'll give you a good reality check on exactly how big the value of this integral should be. So in my case, I see here a rectangle that goes 2 units in the x direction and 3 units in the y direction. So at the very least, I see here that we have an area of 6 on the rectangle. What I'm asking you to do is to compute the volume of the region that lies over that rectangle, but at the same time is underneath the graph of this function. Now, the values of this function can go as low as 0 in this region. If you go out to the y-axis, this is the y-axis over here, when you're on the y-axis, you know your x-coordinate is 0, and having an x-coordinate of 0 does happen in this rectangle. So there are points where this function is going to take on the value of 0. Everywhere else, the function will have on a positive value, but it can't be that big. Seems to me the values of this function here will be, yes, greater than or equal to 0, but they'll be less than or equal to, well, shoot, your x-coordinate can only get as big as 2, and your y-coordinate can only get as big as 6. So the maximum value of this function is going to be 48. And that will be exactly the value of the function right here. When you're at the point 2, 6, the value of the function is 48. So the function is taking values that vary between 0 and 48. That means that the whole thing will have a positive volume, but the whole graph fits inside a box that lies over this rectangle with an area of 6, and it goes up. If I go up a height of 48 everywhere, well, I will have enclosed the entire figure inside this box. So if the whole figure that I'm asking you to compute the volume of sits inside this box, then the volume of our figure is no more than the volume of the box, which is going to be the area on the bottom times the height of the box. And whatever 6 times 48 is, I guess that's 288. That's an upper bound on what the value of the integral is going to be. Please keep yourself from making a stupid arithmetic mistake on your integration problems. Try to see if you can guarantee, for example, that you know the value of the integral is going to be positive, or guarantee that it's negative or something, or get some kind of a lower bound and some kind of an upper bound. And you might kind of eyeball your figure if you can draw it and say, oh yeah, it rises to a height of 48 over here. You could look at what happens on the other corners of the box. There are 2 corners where the value of the function is going to be 0, and on the remaining corner, when you're at the point 2, 3, the value of the function is going to be 4 times 2 times 3, which is only 24. Well, that's half. So I would say that overall, I don't know, we're going to pick up maybe a quarter of the volume of the box, or a sixth of the volume of the box. I would hope it would be at least a tenth of the volume of the box. So I'm expecting an answer which is going to be somewhere in the dozens to the low hundreds. Okay? Just keep that in mind because I haven't worked out the numbers in advance. Let's try to compute the integral properly now using Fubini's theorem, but as a check on our arithmetic, let's see if we get an answer at the end, which is somewhere in the high dozens or low hundreds. Okay? So, here I go. Fubini's theorem. I have to go over this rectangle from 0 to 2, 3 to 6, and integrate the function 4 times x times y, dA. And Fubini tells me that it will be written as the integral as y goes from 3 to 6 of the integral as x goes from 0 to 2 of 4xy dx, and then I put the dy on the outside. By the way, you don't have to put the square brackets in. I find it useful to help me focus on what part of the problem I'm actually working on. You don't have to put in these little statements, but again, I find it very useful to do that just so that you don't plug in the wrong numbers into the wrong variable. So what I would do is to keep everything outside the square brackets unchanged in the first part of my calculation. But now inside the square brackets, I put on my calc 1 hat and say, oh, here I have a function of x. It's a constant times x times a constant. And I have to integrate with respect to x. So I'll use the fundamental theorem of calculus. I anti-differentiate. So it's 1/2 times the first constant times x squared times the second constant. And then I plug in the two values of x, my two endpoints, and subtract. It takes a while just to write all of that out. And when I stick in these two values of x, I'll get 2 times 4 times y minus 2 times 0 times y. So in the end, that comes out to 2 times 4 times y. And that's the function that I need to integrate with respect to y now. So let me just pause and observe that I did get rid of all of my x's. There's nothing left but y's at this point, actually even at this point technically. So this is another Calc 1 problem, and it's easy enough to integrate. Since there is only one variable left, I won't waste a lot of time putting the y's anymore. The antiderivative would be 4y squared. When I stick in these two endpoints, I'll get 4 times 36 minus 4 times 9. So that's 4 times 27, and that's 108. What'd I say? High dozens or low hundreds? I give myself a win on that. All right, so that's Fubini's theorem in action. The concept of taking the two-dimensional shape and chopping it up into small two-dimensional shapes and multiplying the area of every one of those times the value of this function somewhere inside there, please don't lose sight of that concept. But the mechanics of computing the integral come down to just doing a couple of one-dimensional integrals. And as you saw, it's typically the case that you'll compute those one-dimensional integrals by just using the fundamental theorem of calculus twice. Okay, once with respect to x and once with respect to y. Comments or questions on that example?
Could you talk again about how you estimated that it would be in the high dozens or low hundreds?
Yes, I did that by recognizing from the start that what I'm actually computing is, it can be interpreted as, it's the volume of the shape that lies under the graph of this function. So the graph of this function would be a surface in three-dimensional space, right? You know, you should be visualizing z equals 4xy. That would be the graph. And as I was trying to sketch it for you, that's the one that's a kind of a saddle surface in this case. This integral is asking you for the volume of the region that lies under the graph of this function and over the set R that shows up down here. Now, how you estimate that volume, that's up to you. I tried to figure out in advance, first, where did this function take on its biggest and smallest values on this set? And then I knew my integral would be somewhere between the minimum value of this function times the area and the maximum value of the function times the area. I tried to go a little further and just kind of eyeball it and say, what fraction of the surrounding box that I think is actually going to be inside my shape? And that's kind of an art, and I didn't spend a lot of time on it, but it's usually, you know, I don't know, somewhere between 1/10 and 1. But if you really wanted to spend a little bit of time on it, we have talked about this issue of how would you figure out the points inside this set where this function takes on its minimum and maximum values. You could actually go through the whole business that we did before the break. You'd set the first derivative equal to 0, look for points where the gradient is equal to 0. Don't forget to look at the boundary, which might require Lagrange multipliers or something. But in practice, I don't want to spend a lot of time doing that. But yes, my bounds are that the value of the integral will be less than or equal to the area of this times the maximum of that, and it'll be greater than or equal to the area of this times the minimum of that. In fact, let me put that in as a little theorem here. If somebody asks you to compute the integral of some function over any set S actually in the xy plane, so this is, I'm doing the two-dimensional version here, but similar things apply to any set in any number of dimensions. So this is for a function of two variables. Then this integral is less than or equal to the area of S times capital M, and it's greater than or equal to the area of S times little m, where little m and capital M are the minimum and maximum values of the function f anywhere on the set S. Yeah, maybe I should say where. How about f? F. So these are the properties that little m and capital M are supposed to have. Typically, they would be the minimum and maximum values that the function f attains on the set S. So in my case, the area was what, 6, and I found that the minimum value of the function would be 0, and the maximum value was, I think, 48. So that, strictly speaking, it gave me some inequalities on this, but I chose a number that was, I don't know, about a quarter of the way between those two, and I used that as my estimate. So it's a good question, and I really want you guys to get in the habit of thinking geometrically that way, but that's only so that you can prevent yourself from getting a stupid answer here. If you'd have gotten a negative 108, you would have seen that that was wrong. But you wouldn't have known that it was wrong unless you stopped to think about this theorem a little bit. If you'd have gotten 1008, again, you know that that's wrong because of this estimate in here, but if you don't stop to make that estimate, you wouldn't see anything wrong with having an answer of 1008. And I don't want you guys to fall into that kind of a trap. Yang Zhu is asking a question, is this how one defines bounded? You have to be careful with that. There's two uses of the word bounded. You can talk about the function f being bounded. To say that the function f is bounded means that there is a number that goes here. A function f stays bounded if there's some number that you can put here. You guys have certainly had functions that had vertical asymptotes, even back in high school. A function with a vertical asymptote doesn't have an upper bound like that. So that's what it means to talk about the function f being bounded. We've also talked before about what it means for a set S to be bounded. Remember, we had those theorems about a closed and bounded subset of the plane. And in that case, being bounded meant that you could put the whole thing inside some disk. And I didn't use that fact in here, although I am kind of assuming that my set is bounded so that it has only a finite amount of area. Okay, somebody else, Diego, is asking a great question here. Would integrating in terms of y and then x change the value of the answer? And the answer is no. It does not change the value of the answer. There's nothing in Fubini's theorem that actually requires your axes to be called x and y. So if they're called alpha and beta, then Fubini isn't able to say which letter has to come first. you will get a value for this integral. This integral has a value, and if I tell you that it can be computed by this method, then you got to figure, well, it's going to work just as well if I call my axes y and x instead of x and y. So that's a very useful part about Fubini's theorem. In fact, this is what a lot of people think Fubini's theorem actually says. They think it says that you can switch the order of integration, but that's not quite what Fubini is saying. It's just a consequence of Fubini's theorem. So you definitely have problems like this on homework and tests that say, hey, here's an iterated integral, write it in the opposite direction, and then do the computation. And in the way I've got Fubini's theorem set up for you guys right now, that doesn't sound like it's any challenge. All you're going to do is literally change all of the symbols in this region and move them over into this region. And of course, you'll have to swap these two things as well. So if you want, you can just kind of swap the symbols around and you'll get, everything will make sense, and it'll be another integral that also is equal to the original value. So the value of the integral won't change. But I have to warn you that the very next topic is going to be what we're supposed to do in cases where the region of integration is not a simple rectangle like this. And Fubini's theorem can still be applied, and it's very useful. And it's still a good question to ask of maybe, should we interchange the limits of integration? And the answer is sometimes yes, but doing it is a little more complicated than just swapping the symbols that you see here. I'll show you when we do it. Probably won't get to it today, but you'll have to be drawing some pictures first and then kind of looking through them and making a decision about what your limits of integration are. In fact, let me make this point clear. I set Fubini's theorem up for you in such a way that the rectangle came to you with these four numbers given. And then what Fubini's theorem says to do is to just write these four numbers into these four little slots. But I want to describe the process a little bit differently. I could have just said, hey, here's such and such a function of two variables, and let me draw you the region over which I want you to do the integral. In that case, what you're writing into these two spots asks you to do the following things. You need to go roaming around the set R, scanning all the points that are in the set R, and asking all of those points about their y coordinates. And what you're writing into these two positions are the least and the greatest values of the y coordinates that are found anywhere in this set. Similarly, on the inside integral, you're going to wander around all the points inside the set R and ask them about their x coordinates and write down the least and the greatest values of the x coordinates anywhere inside the set. Get used to thinking about it in that way, because that's going to be the recipe that we're going to need when the set R is not a rectangle anymore. I'll show you that example in a second. So just for clarity, though, in the outer limits of integration, we're talking to all the points that are in the set R, and talking to all the points about their y coordinates, and the minimum and maximum y coordinates go into those two positions. When we go to the inner integral, in the inner integral, we're treating y as a constant. You need to think about holding y as a constant inside the square brackets. If you hold y constant in the xy plane, that forces you to lie on a horizontal line. And really, I know you see the a and the b here, and I talked about how they're the min and max values of x. But the way you need to get used to thinking of it is, when you moved into the inside the square brackets, you held y constant, which now restricts you to being on a single horizontal line segment. And at this point, you should now be talking only to those points, asking them about their x coordinates, and writing down the least and the greatest values of the x coordinates that you see anywhere in that set. I know that's a lot of words, but you'll see that it'll be very important in the next example. Well, let me not move into the next example. Ask me more questions about this example or anything that you think you might be doing with a rectangle lined up like this way. Is there any part about this that's unclear? All right. That's section 5.2. let me start to show you what we're going to do in the next section, 5.3, and that's what we're going to do in the case where R is not a rectangle. So to illustrate that one, let me do the specific example that we had in a previous problem. Remember last time you guys were asking me about this kind of a shape, where somebody had drawn a parabola in the XY plane. The XY plane, remember that's just the thing that's spanned by the Y and X axes. So that's the set of points where Z was equal to 0. So everything so far that I've drawn, except for that line segment right there, well, everything else is just taking place in the XY plane. And then they asked you to start drawing some funny shape that consisted of making a bunch of triangles resting on top of this. Okay, well, I don't want to do a bunch of weird rectangles in this, sorry, a bunch of weird triangles in this case. Let me take something simpler, like let's just elevate a plane. How should I make it go? Yeah, you know what? I'm just going to try to raise a plane like this. So now I'm making a three-dimensional shape. Oops, sorry. That it has a parabola on the bottom, and then a single plane is its roof line. And I want you to figure out the volume of the shape that's inside there. So let me give you a particular example. To make a plane that has the x-axis in it, I might choose an equation like, let's just have z equal to x. No, how about z equals 6x? How's that? Okay, so that would be a steeply rising plane that lies on top of this parabola. And if I ask you to integrate that function with respect to area over this region, and I'll just draw the bird's eye view for you here. So that's now the shape that's bounded by this parabola, y equals x squared. And I forget what the end line was. Y equals 5, maybe? I don't remember what we did last time. So we've got this thing that looks like, you know, a fingernail, and that's a part of the xy plane, and it's bounded by this curve, parabolic curve, and by this straight line. If I want to get the volume of the region that's under the graph, it's under the plane, and at the same time it's over this parabolic region, that volume would be calculated as this integral. So you're chopping this region up into a lot of little pieces, and then you take this as the measurement of how high you should go at each point, and you add together the area of the little tile on the bottom times the height of how tall that little region would be. And height times area would give you the volume of such a box. You add together the volumes of all the boxes, you get the total volume of the whole set. Okay, so that much is me just talking about the principle of integration. Now let me use Fubini's theorem. You can't use Fubini's theorem right away because that region is not a rectangle. But you can still use the same principle if you think about the words that I was saying when I wrote down this double integral. So let me show you how this works. To use Fubini's theorem, I'm going to write this as an iteration of two one-dimensional integrals, one of them with respect to y and one of them with respect to x. The function that I'm going to integrate is exactly the function that I was given. But if you've been given a formula for this function of x and y, just write it down. Since you have the variable y showing up on the outside here, you need to put the limits of integration for y on the outside here. And likewise, x is coming next on the inside, so I'll put limits of integration for x in there. You're going to put a couple of numbers into these two slots. And those numbers are supposed to ask for the largest and the smallest values of the y coordinate that are found anywhere in this set. Now, I've drawn this thing kind of sideways because that's the way it looks over here. I guess traditionally we put the x-axis this way, the y-axis goes that way. Here's the parabola, y equals x squared. Here's the line, y equals 5. Okay. Now, what I need you to put into that spot and that spot are the least and the greatest values of the y coordinate that are found anywhere inside the set. Which way do you go to get your least y coordinate? North, south, east, or west? Oh, nobody wants to talk. Well, fine. You get your minimum y coordinate by going as south as you can. And in this picture, this is the southernmost point that you would find anywhere in this figure. So that's going to be the point that has the smallest y coordinate. What can you tell me about the y coordinate of this point? Seems to me this point is right there on the x-axis. The x-axis is the set of points where y is equal to 0. So this point must have a y coordinate of 0. In the same way, to fill in this box, I need to scan the whole set and talk to all of these points and ask them about their y coordinates, but I want to listen for the greatest y coordinate that I'll get. And the way to get your greatest y coordinate is to go as far to the north as possible. And if I'm stuck inside this set, that means any one of these points would be giving me the largest answer. And the answer that they're going to give me for their y coordinate is, their y coordinate is equal to 5. So those are the numbers that I put into those two boxes. I'm going to do something similar when I go to fill in these two boxes, but you have to remember not to scan the whole set looking for the biggest and least and the greatest values of the x coordinate. I mean, let me just do that as a warm-up, but that's not going to be what I'm going to use to fill in these two boxes. If I did ask you to find the greatest x coordinate for any point in this set, again, you'd be talking to all these points, asking them about their x coordinates, but to get greater x coordinates, what you should do is go as far to the east as possible. I see one point that's the eastmost point. That point is the intersection of the parabola y equals x squared and the straight line y equals 5. So those are two things that I know about that point. And that point has two unknown coordinates. So I'll have two equations in two unknowns, and I should be able to solve these two equations in two unknowns to figure out what the values of x and y are. Obviously, I already know what the y coordinate is, but the x coordinate, well, it's got to be a square root of the y coordinate, and since we're on the right-hand side, we know it must be the positive square root. So that's the greatest x coordinate that I find anywhere in this set. And likewise, the negative square root of 5 would be the least x coordinate. But those are not the numbers you need to put into these boxes, because as you move to the inner integral, you're supposed to be holding y constant. The set of points that have a fixed value of y, a constant value of y, is just a single horizontal line. And what I need to put into these two boxes now are the answers to the question of the least and the greatest values of the x coordinate, but not for the entire set that was given, only for the part of that set that has a fixed y coordinate. So you need to look only at these points where the y coordinate is some number, not necessarily 5 or 0, but some other constant value. Now, if you are stuck on that line segment, if you start talking to all of those points, asking about their x coordinates, it's still true that you'll get your least and your greatest values by going as far to the east and the west as possible. But getting the point that's the eastmost point, now that's a point that's on the parabola y equals x squared, and it's on this horizontal line y equals c. There's your two equations in the two unknowns x and y. You can solve for the values of those two coordinates. What you're going to get is, well, y is still equal to c, but the x coordinate will be the square root of that c. And I don't know exactly what the c is because I don't know which horizontal line I'm stuck on. As I move from the outer integral inward, as I move inside the square brackets, I'm holding y constant, but I don't know what the constant is, so I'll just call it y. And that means that my limits of integration will now be written as the square root, sorry, it'll be a negative square root of y for this one, and the positive square root of y for that one. So this is you using Fubini's theorem on a non-rectangular region. It's the same recipe, but it has the consequence that when you try to write down your limits of integration, you will have constants for those two limits of integration. But these two limits of integration will express the inner variable of integration as a function of the other variable of integration. So in our setting, this is how the calculation is going to go. You'll still keep all of this stuff unchanged. But to evaluate this inner integral now, I need to treat everything that's not an x as a, well, there's no y's in here. So I'm going to integrate this function of x between those two values of x, which are temporarily treated as constants. You should use the fundamental theorem of calculus. That antiderivative would be 3x squared. Something is wrong here. Let me complete the calculations. I just realized what I did wrong. Nothing wrong so far. It's just I didn't label my picture properly. When I actually evaluate what's inside the square brackets, what I will have will be a function that has no x's left. You see x is here, but I'm about to plug in those two values of x and subtract, so there will be no x's remaining. All that will remain is a function of y, and then I will integrate that function of y between these two values of y, and I will get a number. It's a little odd in here because when you actually stick in these two values of x, what you're going to get will be a 3y for the first one, and when you square this, you'll also have 3y, so when you subtract, you're just going to get 0. And when you integrate 0, you get 0, which is a number. It sure doesn't look like it's the volume of this figure. That doesn't look like it has a figure of a volume of 0. Does anybody see why? What's wrong with my picture? Or what's wrong with my formulas? Maybe I should have said it that way. Anybody see? Yeah, Yang What are they?
I think the expression should be z equals to 6y instead of the...
Yes, yeah, exactly. I just now noticed that when I had to go looking for a problem. This formula does not reflect what you see in the picture. The value of the function, the z coordinate, is increasing as you move with increasing y's. I should have written this thing as a 6y. So sorry about that. You could go ahead and you can calculate the integral of 6x. The graph of the function z equals 6x would be a plane that includes the y-axis. It's tilted above the x-axis, but it includes the y-axis. And that integral would just have just as much volume above this half of the parabola. You would be above this half, and you would be under that half. And so the contribution from this integral would negate the contribution from that integral. So that's why we got a 0. If you do want to know how much volume is in there, you have to repeat these calculations where these x's change to y's. Nothing changes here. All that stuff is still the same. But at this moment, you would be integrating 6y with respect to x. That antiderivative would be 6xy, right? Because 6 is a constant and y is also a constant. So you have that constant times x. And now when you stick in these two endpoints, what you will get will be 6 square root of y times y minus 6 times the negative square root of y times y. Which comes out to be 12 times y to the 3/2 power. And that's what you need to integrate as y goes from 0 to 5. And now you won't get 0, but you'll get some other number. So I apologize for having a formula that didn't reflect the picture that I had drawn, but the principle of how you compute these integrals is the same in both cases. Okay, I've gone over. Do you guys have last minute questions you want to ask me? All right. Try whatever homework problems you can do. Ask me about them next time. And actually, next time we'll probably just spend most of our time working through examples like this. All righty, guys. Thanks for coming, and I'll see you in 48 hours.